I wonder what you would say to the so-called evidence that the universe is flat. If they are correct, would that show geocentrism is wrong since geocentrism requires a spherical universe? I know that they determine the shape of the universe by its density, but are there other ways to show the shape of the universe? And what about the distribution? If I recall correctly, I remember you saying that one side of the universe has more mass than the other, which will aid the rotation and precession of the universe. Do you have some references for that? Yes. Oh, gosh, what's her name? Anyway, that's why I need to make a 10th edition of geocentrism. Let me see, geocentrism for dumbskis and geocentrism 101. There are now we are but I already covered a little bit in geocentrism 101 with Longo. Dr. Longo from the University of Michigan has found not only is there um, a lopsided mass distribution in the universe with more galaxies on one side than the other. You also have spin rotation clockwise for like 2/3 of the galaxies, which should not be for a Big Bang universe. Those spin rotation directions should be completely random, but they're not. They're all mostly right-handed, clockwise rotation. So, like somebody designed it that way. And then he also designed putting more galaxies on one side of the universe than the other. You can even see this in the SDSS picture of 2005, where you have the Great Wall of galaxies. Okay. Well, that Great Wall is on one side of all those galaxies that they mapped. And it looks lopsided. Okay. So Longo was the first guy. And then recently, there's been a team headed up by a woman, Anna Rothami or something. I forget her exact name. But that has been put in some of my recent videos. Okay. And so there are actually 3 different sources. There's another guy who wrote a paper on this and saying the same thing, finding the same evidence that the universe is lopsided. And what does that do for geocentrism? It just makes it even better. Because in our geocentric universe, we have the Earth as a center of mass, and the universe is precessing around this center of mass. Okay? In other words, it's in a wobble. And you know, when you put too much mass or weight on one side of a spherical rotating object, it's going to wobble, just like your car tire wobbles if you got too much weight on one side, right? So it's going to wobble. It's going to have a cycle to that wobble. It's going to determine what the mass is, what the spin rate is, what the distance it has to travel is, and it's going to have a cycle to that wobble. And guess what? That cycle determines our seasons. Right, because the whole universe has to go up and down 47 degrees and it's carrying the sun with it. And that's what gives us the different positions of the sun in the sky that's going to determine our seasons, you see. And there's also there's a vertical wobble and there's a horizontal wobble. Together, they form a spiral. The universe spins in a spiral. And it can do that because it's a little lopsided, you see. but it's not lopsided too much so that it would go out of whack, because you know what happens in your washing machine when you put too many clothes on one side, or your dryer. Well, maybe not the dryer so much. The washer does it because the clothes get wet and heavy, and so you put too many clothes in the washer, and that thing starts to wobble. And if it's too much, it's going to wobble right off its foundation. Sometimes if you just have a little more weight to one side in your washer, you'll get a little wobble, but it won't, take it off its foundations. So all this is good for geocentrism, you see. See, we have the best universe. That's hands down. We just have the most functional, simplest, most stable universe. We don't have the problems that the Big Bangers do, because we have an enclosed universe that rotates. And you're not going to get many problems with that kind of universe. But if you have a universe that's expanding, oh, baby, you're just inviting trouble, because you got all these open-ended things that you have to answer now. See, a circle is enclosed. Sphere is enclosed. Okay? The only problem it's going to have is internally, and there are a few, because the universe rotation controls everything that's inside of it. But if you have something that's open-ended and still expanding and accelerating and all that, you're going to have big problems. That's what they do today. Okay? So God gave us the simplest Occam's razor universe that was possible. And that's why it works so well. Okay? Now, this other question, I wonder what you would say to the so-called evidence that the universe is flat. Yeah, you'll hear that term a lot. Okay, but it has nothing to do with the spherical universe. Okay? Flat is the term they use for a Euclidean universe, three-dimensional universe. Okay? They really want the universe to be Euclidean, because that really works well. That's the one with length, height, and depth. Okay? Because they've been working with this Riemannian two-dimensional universe ever since Hubble. And that's what's given them the problems. Because it doesn't work very well. As you could probably guess, if you live in a world that has 2 dimensions and not 3, yeah, something's missing. Okay? And that's why they want to get to a flat universe. Just their terminology. And we're going to go through this. I'm going to read some of my material from Galileo Was Wrong. And if you ever get the chance, you should read it. Page 250, objection 22. And I'm going to read excerpts from that right now to help you understand this a little better, why they choose flat universe. See, because the geocentric has nothing to do with Riemannian geometry. We don't have to use little fudge math like that to make things work. We just assume everything's Euclidean and go from there. And it works very well. As I say again, the problem began when Edwin Hubble, 1929, looked through his telescope and he saw that all the galaxies out there, not the local ones, the ones far away, all had redshift. And if they all have redshift, everywhere you look, that means what? That you're in the center. You're in the center of the observation point. Because if you weren't in the center, then you would see some of those galaxies have blue shifts. Because that's the way the light travels to us. Okay? So if you're a atheist, non-Bible believing man who hates God and hates the Catholic Church, and you see every galaxy with the redshift, what are you going to do? Well, you're going to try to make a story that you're not. Because if we are in the center, God help us, because that means he put us here. And so let's do this. Let's use Riemannian math, get rid of Euclidean math, and we'll make a surface, balloon surface, and we'll put all the galaxies on the balloon surface. And then we'll expand the balloon. And what is each galaxy going to see? They're going to see redshift. And there we have our answer to why we see redshift, because we're on the surface in the Milky Way galaxy, you see. So that's where all the problems started. Okay, once you start using a Riemannian two-dimensional universe, you're stuck with it. Okay, so now we have to explain how the Big Bang can get out of all the problems it has and get back to a flat universe, a Euclidean universe. Well, good luck with that. Okay, and I'll show you why as I read some of this stuff for you. Now, look, this is heavy science. Okay, so some of you, of my dear patrons, are going to be going, because you don't understand this stuff. But I think it's good that we get it out there, because there's just a lot of things they're doing today that they float right by people, and the people don't know any better. And you're saying, well, they're scientists, they must know what they're talking about. No, they haven't the slightest clue what they're talking about. Okay, that's where you got to get. Let me see, where should I start? All right, maybe let me just start here. And then one thing they commonly do is they try to draw on Einstein, Albert Einstein, to be the doctor to fix everything for them. Okay. And that's where I'm going to start right here. The draw to Einstein is very great in modern cosmology. Since he is propped up as such an authority, the temptation to trace current theories to his theoretical foundations is quite common. The truth is, however, that the only commonality that modern dark energy theorists have with Einstein is that both invented what they needed to permit their theories to work as they wanted them to work, and both were motivated to do so in order to preserve the reigning cosmological paradigm from which they were spawned, the Copernican principle. Now, what's the Copernican principle? I made a whole movie about it back in 2014. That's the idea that the Earth is not special and is in no special place of the universe. It's just a speck of dust like everything else in the remote recesses of outer space, and we don't know where it is because there's no signpost saying, here you are. See, it's not special. So they want to preserve the Copernican principle. That's what all this is about. Why? Because if we can get the Earth out of the center, we have a good chance that God doesn't exist. And if God doesn't exist, that means I'm not going to be judged for my sins. Yeah, that's what it's all about, believe it or not. The real truth is that Einstein's classical general relativity can only account for the 4% of the universe. I got a typo there. Only account for 4% of the universe, since the universe is now claimed to be 96% dark energy and dark matter. And if they still wanted Einstein to be their mentor, they needed to make Einstein's theory come up to snuff. They then decided to inject it with a booster shot called lambda. It's another fudge factor, which is 73% of the 96%. And the two are given the acronym LCDM. Did you ever see that? They call the universe an LCDM universe. Well, the L is lambda that they put in there as a fudge factor. And then CDM is cold dark matter, in case you were wondering. However, adding lambda to general relativity's original tensor equation caused a huge problem. It required that they redefine general relativity, since it does not work with lambda. That is, unless lambda equals 0, general relativity cannot add up its tensor equation. Then I have a whole footnote explaining what that means. And just bear with me. This takes us back to the basic problem with modern cosmology. The Big Bang, in opposition to steady state cosmology. Now, what was that? Steady state was the theory before the Big Bang, where they believed that everything is infinite and steady. It doesn't change. That's how we can explain the origin. You don't have to explain something that's infinite. That means the origin's already taken care of, so to speak. And you don't have to explain anything going on in the universe because it's all static, you see. And of course, that all changed with the Big Bang because now everything's moving. Okay? This entity is said to have been spawned from a previous universe, and that universe from an even earlier universe. This is the Big Bang theory, by the way. All right. As if getting something from nothing is not enough of a problem, the second thorn in the side of the Big Bang appears when the rate of the explosion must be determined. If it's too slow, the universe will go into what is called the Big Crunch. That is, gravity will pull all the exploding parts back together before it can evolve into an organized biophilic system that we see today. If it's too fast, that is, the explosion is too fast, the universe will be diffuse and likewise will not be able to produce galactic structure and biological life. Like Goldilocks and her porridge, the expansion must be just right. Otherwise, life couldn't exist, at least under modern science's illusory belief in evolution as the mechanical process that produces life. To boot, the amount of matter in the explosion must also be just right. Too much, and the universe will not expand. Too little, and no complex structures will be formed. You see what problems they have? It's one thing to say that God didn't create everything. It's another to try to explain how you're going to put it all together. And they've been trying since this theory was adopted, 100 and so years ago, and they still haven't been able to do it. They're no better off today than they were 100 years ago. So let's move on here. I hope I'm not boring anybody, but after a while, I'll just cut it off and I'll take questions on the chat room here. Where was I? Too much in the universe will not expand. Too little and no complex structures will be formed. As one scientist put it, it's like trying to balance a pencil on its point. As one can see, modern cosmology is in a real pickle. But it didn't start here. When Newton discovered gravity, one of his first problems was having to deal with Copernicus's limited universe. Newton realized that the very gravity he discovered would eventually pull the stars into one massive ball. In order to compensate for this problem, Newton opted for an infinite universe. As time went by, science realized there were too many problems with an infinite universe. So Einstein tried to compensate for gravity by introducing an opposing force, which he called the cosmological constant. It was just a figure he put into his, tensor equation. That's all it was. His new theory would reverse the effects of gravity and keep the universe from falling in on itself. The universe would remain static, not expanding or contracting. It would also follow Mach's principle, wherein space was defined by the matter within it. But Wilhelm de Sitter didn't follow Mach's rules and created a variation for Einstein's cosmological constant. De Sitter ignored all the matter of the universe and only concentrated on its quantum energy, an energy that would be enough to propel the expansion of the universe. So the choice was between Einstein's static but matter-filled universe and de Sitter's expanding but matter-deficient universe. Next, Alexander Friedmann then fiddled with Einstein's math and eliminated the cosmological constant and produced an expanding universe still under the constraints of general relativity. So relativity was saved. But this required that he make the equations produce a universe whose matter was spread out evenly and was the same everywhere. And that's the terms you often hear called isotropic and homogeneous. Okay? So in order to save general relativity, it had to be isotropic and homogeneous, otherwise known as the cosmological principle. This made Arthur Eddington backtrack to point out that even with the cosmological constant, an Einstein-type universe was not really static or balanced. Since gravity and Einstein's cosmological constant had to be balanced so perfectly, like balancing a pencil on its point, even minute fluctuations would produce a runaway expansion or an unstoppable contraction. You see the problem. Unless you get it just right, the Goldilocks universe that they haven't been able to find, once it's expanding, it's just going to go on forever. And any glitch in it's going to make it even faster. And if it's the other way, then it's just going to contract and go up into a ball. You know? And if it's so old, as they say, this should have happened a long time ago. But you don't get that in a geocentric universe. We just don't have these problems. All right. As NASA puts it, quote, Einstein first proposed the cosmological constant as a mathematical fix to the theory of general relativity. In its simplest form, general relativity predicted that the universe must either expand or contract. Einstein thought the universe was static, so he added this new term, lambda, to stop the expansion. Remember, who's the guy who told him that you have to have the expanding universe? You discovered him. Hubble. And why did he want an expanding universe? Because that way, if you put all the galaxies on the surface of the expanding universe, they're all going to see redshift. So now we have an alternate explanation for redshift other than the Earth being in the center of it all. So you see how that caused problems. They're still trying to figure it out. Okay? Friedmann, a Russian mathematician, this is still the quote from NASA. Friedmann, a Russian mathematician, realized that this was an unstable fix, like balancing a pencil on its point, and proposed an expanding universe model now called the Big Bang Theory. In retrospect, when Hubble relieved some of the problem by interpreting the redshift of galaxies as a sign that the universe was expanding, still, in order to have the matter move, yet, you know what, this is just getting too, I've got pages here to read that are very important, but, I don't know if I should keep going. Let me just read 2 more paragraphs and then we'll stop. And then we'll get to your questions. In retrospect, when Hubble relieved some of the problem by interpreting the redshift of galaxies as a sign that the universe was expanding, still, in order to have the matter move yet remain homogeneous, as required by Friedmann's equation, the value of its rate of expansion, h, as well as, that's called the Hubble constant, by the way, as well as the value of its density, omega, and the energy to propel the expansion, lambda, had to fulfill the Goldilocks rule. It had to be just right, or there would be no universe. Various scientists have spent their entire careers trying to figure out the perfect combination to these three numbers, H, omega, and lambda, but to no avail. Again, it is like trying to balance a pencil on its point. This is what happens when the universe is made to start from a big bang instead of a creative fiat. The math never produces what we actually see. Postulating a big bang is easy. Making it work with all the other laws of science is quite impossible. All right, so yeah, we're getting into really technical territory here. But if you're interested in all this, get Galileo was wrong. Question 22 on page 250. There's 10 pages to that. So I only bored you with about 3. So at any rate, let's get to your questions here. We got a whole hour for you. So